Hey guys, welcome back. Today we're going to be talking about the ocean floor. We've been talking about largely the rocks that we find on the continents. We've talked about a lot of rocks that we find on islands. We've been talking about volcanoes, metamorphic rocks, all of these things. But the one thing that we haven't spent a lot of time talking about, except in passing, is the ocean floor. And the reason why we haven't talked a lot about it is because the ocean floor is, well, it's at the bottom of the ocean. It's kind of hard to be able to demonstrate these things with really good images. It turns out that the bottom of the ocean is very, very dark. It's very hard to get information from the bottom. When ships get lost at sea or airplanes get lost at sea, sometimes they're never found. Amelia Earhart famously disappeared in the Pacific Ocean, and her aircraft was never found. Here we actually see a ship that was found after it wrecked, but notice that it's not in a dark area. It's in a nice shallow area, and so it can be found, and people can actually dive on it. These are divers over here diving on the ship. But this is an abnormal situation. For the most part, the seafloor is a mystery. Scientists will tell you that we know more about the surface of Mars than we do about the bottom of our own oceans. And that's actually true, because the surface of Mars is not covered with water. It might have been at one time, but it isn't currently. Okay, with that said, let's go ahead and dive right into talking about the ocean floor, because that's 71% of our planet, its surface, and we haven't spent a lot of time talking about it. So the ocean floor has a really cool structure. It's kind of a repeat structure all over the world. So we can actually look at one or two oceans, and we kind of got the idea of what's going on. And one of the best places to look at is the Atlantic Ocean. The Atlantic Ocean has all of the different features that all of the other oceans also possess, except for one type of feature, and we'll talk about that as a special case. Well, first off, we need to note that all of the major ocean basins have three major provinces on the seafloor. There's basically the continental margins, which is where the ocean laps up along the continents. Here we see it in Africa and North America. The deep ocean basins. The deep ocean basins are here and over here, this deeper part, this deeper blue color. And we can see this also in the topo, or in the bathymetric profile that we see right here. Here's a deep ocean basin, here's a deep ocean basin. And of course the oceanic mid-ocean ridge, which is going to be located right here in the middle. There are other kinds of ridges. We're going to talk about those ridge systems briefly. But notice that the mid-ocean ridge is actually a mountain chain on the bottom of the middle of the ocean. Now, this is not what people would have expected if you were actually out in the middle of the ocean and you were looking for probably the deepest point. You'd make the assumption that the deepest point might be somewhere right in the middle. Plate tectonics has kind of put that on its head. It turns out that the shallower points of the ocean are at the edges, right here at the continental margin, right where it laps up onto the continents, which is to be expected, of course. And in this case, in the center of the Atlantic Ocean, right here. Not necessarily would you think it would be over here or over here. In fact, the deepest part of the North Atlantic is right over here, just east of Florida and Cuba. So there's two kinds of continental margins, passive margins and active continental margins. We're going to talk about the passive margins first. And in this case, we can talk about passive margins because this is the one type of province that also exists right here. Here's a continental margin, here's a continental margin. And so we're really talking about something similar to what we see right here. So here we see the oceanic crust. It's connected to the continental crust, and it's actually all a single plate, but it's one plate that's composed of two different kinds of crust. And so when it transitions from the continental crust into the oceanic crust, in this case, this is all the North American plate from here all the way into North America. We see that there's got to be a transition also from continental topography into the oceanic topography that we see here where it drops off. And in that transition, there's basically a continental shelf that has been deposited here. And basically, these vary greatly in width. Sometimes they're really, really wide. Sometimes they're very, very narrow. When we come over here, we'll notice that what we see over here off the coast, east coast of the United States is much wider than what we see off the west coast of Africa. They have features like submarine canyons, and these submarine canyons can distribute sediments well out into the deep ocean and form deep sea fans. This is actually common in all of the oceans, but the biggest deep sea fans are actually in the Indian Ocean. Basically, they're deposits that are coming off of the Ganges River and the Indus River as well. And so we see the shelf up here, it's nice and flat, and then it breaks into a slope. And then it changes into a rise. So the way that this is actually thought of is, imagine coming off of the seafloor, you're going to rise up, and it's going to come into a sudden slope, and then you're going to deposit yourself right up here onto this shelf. The shelf is actually a pretty shallow zone. And then, of course, the transition between the shelf and the slope is something called the shelf break. This is something that in oceanography class, we spend a lot of time discussing. So if you're interested in submarine basins or in oceanography in general, that is a class that you should also take in supplement, of course, to the geology course. Why do we care so much about them? Well, they contain important mineral deposits. And if I was to say important, I would say extremely important. Think of oil. Oil is a huge factor. Some areas are mantled by extensive glacial deposits. And so in that case, you would get glacial deposits along the shelf and maybe along the slope here during times of ice age, when the glaciers would actually protrude out into the ocean. And we do actually, in fact, see evidence of this all the way as far south as New Jersey and in some cases probably Virginia on the East Coast. It marks the seaward edge of the continental shelf. So here we see the continental shelf here, and here we see the slope, and it's right at this shelf break that we usually define the edge of the continental margin, right? So this is where we say the continental margin begins and ends, is right between the shelf and the slope. The slope itself is a relatively steep structure. It's the boundary between the oceanic crust and the continental crust. So, I mean, that's kind of implied. It's not directly above, but we usually kind of think of it that way. And usually there's a series of faults. These are faults actually that are stepping down the continental crust as it combines with the oceanic crust. It's found in regions where trenches are absent, right? So we haven't talked about trenches too much other than in the plate tectonics lecture we gave quite some time ago now, towards the beginning of the lecture series. So if you don't remember our discussion about plate tectonics, go and find that video and watch it again if you're kind of dusty on that, or rusty, I should say, on that subject. The continental slope merges into a more gradual incline, the Continental Rise. So here's the rise down here, and it's a thick accumulation of sediment. There's a lot of oil and a lot of mineral deposits all over in this area. At the base of the continental slope, turbidity currents deposit sediment that form deep sea fans. Okay, we've talked about all of this. So you guys have the kind of the structure down. Now the real question is who owns this, right? Who owns this shelf? There's a lot of oil in here. Who owns that? And so there's a whole kind of genre of legal thinking and approach to the who owns the sea and who owns the sea floor. And it has actually sparked conflicts and wars in the past, and it will almost certainly spark wars and conflicts in the future. But anyways, where you define, for example, if China was to begin drilling here right off the coast of Virginia, would that make Americans very happy, or the Russians, or if they were to do this? It's a controversial thing, but how far out into the ocean do you technically own it? So this is a kind of an interesting question. In contrast with the passive continental margins or the active margins. And active margins are basically areas where you either have a strike slip fault like the San Andreas fault that is moving side to side, or, and we'll be talking about those kinds of faults in the next lecture, or you'll have a subduction zone. So in this case, the continental slope descends abruptly into a deep ocean trench. So here we see the continental plate, and notice that it just goes straight into this trench. The trench is located right here. And so we see the seafloor spreading occurring here at the center. We're going to come to this here in a couple of slides and describe what's happening here. And the plate is being subducted beneath the continents. And we've been kind of giving a general idea of why this might be happening. The oceanic plate is more dense, and it will tend to fall underneath the less dense continent. Accumulations of deformed sediment and scrapes of oceanic crust form accretionary wedges. So as this goes down, this is basically right along the trench. The trench is acting like almost like a razor blade. And so it's scraping everything that's going from the oceanic basin down into the subduction zone along this trench here. And so as it's going down, you're accumulating a whole bunch of stuff right in this area here. That's also a good place for minerals. And that also extends the continent out into the ocean somewhat, especially over time. And so here's a cross section of what I'm trying to talk about here. Probably a little better picture than the previous one. So here we see a mid-ocean ridge. There's a rising mantle plume that's coming up. And so here we see a piece of oceanic lithosphere, or oceanic crust that's actually subducting underneath the continent. Here we see the volcanism. This is all stuff that we know about. But this is what I wanted to show you. Here are those scrapings. So all of this stuff starts depositing, all this sediment starts depositing on the oceanic crust, but it doesn't all necessarily make it down all the way into subduction zone. It gets scraped off as it's on its way in. And so you get these large, very complicated sheets of sediments that wind up getting in place between the continent and the subduction zone. And so the trench is actually located usually at the front of this. Good places where you would find large accretionary wedges would be northwestern California, for example, certain parts of China, and it's actually a pretty common occurrence in some of the Southeast Asian areas. So here's some other features. So the trenches usually are these relatively narrow features. They're not very big. So here's the Mariana Trench in the West Pacific, and you notice it's not very wide. It's this long line right here. The deepest parts of the ocean are in these trenches. So here's the Challenger Deep, for example, which has been generically assigned the deepest point on Earth. Some people have contested that there are deeper points, and that's fine, but just know that this is the deepest point on Earth. It's out in the middle of the ocean, but notice that it's actually near the Mariana Seamounts, and the seamounts actually, Guam and Saipan, actually come up all the way out of from the seafloor all the way up to the surface. Most are located on the Pacific, or in the Pacific Ocean, right? There's tons of subduction happening in the Pacific, and there's not a lot happening in the Atlantic. If we go back over here, see if I can get that picture back. There it is, the Atlantic Ocean. Notice there's no subduction zones here. So the Atlantic Ocean is doing nothing but widening. But in contrast, the Pacific Ocean is doing a lot of subducting. So by comparison, the Atlantic is growing and the Pacific is shrinking. Okay, so eventually North America and Russia, or the Eastern Asian continent, will be coming in closer proximity with time. Sites where moving lithospheric plates plunge into the mantle. So basically this is going straight into the mantle and it's associated with volcanic activity. The seamounts here from Guam, Saipan, all these seamounts that basically trend up towards Japan are volcanic islands. They wouldn't exist if they weren't volcanoes. Another kind of cool feature about submarine basins are abyssal plains. A lot of people thought that the bottom of the ocean was this big flat abyss of nothing. You know, the word abyss is a Greek word and it means bottomless pit, or, you know, it's usually translated as bottomless pit in a lot of the old Greek texts. It basically means bottomless. But when you go to the bottom of the ocean and you happen to go into an area that's full of sediment, you find an abyssal plain. And so right here off the coast of the United States, there's actually a really nice abyssal plain between the Mid-Atlantic Ridge and the Continental Rise. Okay? And so here we see the abyssal plain here. We're going to come to these features here in the next slide. Like likely the most level places on Earth. You know, think of it as like the Great Plains of the ocean. They're very deep and they're very flat. They are sites of thick accumulations of sediment. You know, we have all these big subduction, or not subduction zones. We have very large submarine fans that are being deposited across the abyssal plain off of these shelves. Right along in this area, and then we also see a lot of other stuff being deposited into these basins in kind of a complex series of mechanisms. They're found in all the oceans, so they're all over. It's a common feature. There's an abyssal plain here in the North Atlantic. There's actually several. There's another one over here. There's another one down over here. And of course, as you go deeper and you get older in the crust, you end up getting more abyssal plains. Seamounts are isolated volcanic peaks that exist on the bottoms of the oceans, and many form near oceanic ridges. So here we see the Mid-Atlantic Ridge. There's a bunch of seamounts down over here, but notice there's also the New England seamounts located just adjacent to that abyssal plain that I just pointed out. These are the same seamounts there that we see here. Okay, so there's an abyssal plain here. There's that abyssal plain again. The New England seamounts right there. And so we also find seamounts all near the Mid-Atlantic Rise. or Mid-Atlantic Ridge, I'm sorry. They may emerge as an island. That does happen. Bermuda is presumably one of these cases. They may sink and form flat tops, seamounts that we find on the bottom of the oceans. These things are actually pretty common. And they're basically vast outpourings of basaltic lavas on the ocean floor that create extensive volcanic structures called oceanic plateaus. They basically start off as very, very, very large island complexes in a lot of cases. The island chain of Hawaii, for example, is similar to this. The big island of Hawaii is this very, very, very large place. There's several volcanoes nested together, but eventually the wave action and weathering is going to take place. It's going to bevel off the entire top of the island, and it's going to be a nice flat top. And over time, the oceanic crust actually gets older and it gets colder, and that makes it subside down into the ocean with time. So at some point, the big island of Hawaii will be under quite a bit of water, and it will be a flat top structure, a flat top seamount. So the last of the features that we really need to know well are the oceanic ridges. These are basically broad linear swells along divergent plate boundaries, and they occupy elevated positions. So here we actually see a basin. Here's the shelf. Here's the slope. Here's the rise. Here's some seamounts. You'll notice that's a beveled off. It's a flat-topped seamount. And right over here we see a mid-ocean ridge. Here's an island that's actually poking out right above the water. Basically, there's extensive faulting, and there's lots of earthquakes there. High heat flow, because this is an area where the mantle is coming up and creating crust because the crust is being pulled away. And so the interaction between the seawater and the mantle and all of the Earth's heat right along this zone here are basically forming new crust as quickly as the Earth can convect the old crust away. That's a lot of rock every year that it has to do that to. There are numerous volcanic structures. And when I say numerous, I mean tens of thousands of different types of volcanic structures. And I don't mean just volcanoes. There are undersea lava flows, there are cracks, fissures, there are undersea volcanic faults, there are geysers, or I should actually call them black smokers. We're going to be talking about all of these here momentarily. What are the kinds of features that we see? Well, first off, the major thing that we need to know about these oceanic ridges is that they're very, very huge structures. They're all interlinked one with another, and they go from basin to basin. And in fact, they're the largest topographic feature on Earth's surface. They're by far the largest topographic feature. They're over 43,000 miles in length. That's 70,000 kilometers. And that's 20% of Earth's surface, just in one single feature. That's incredible. And they wind through all major oceans, And the only one that the only minor ocean where I would say you wouldn't see a whole lot of this would be in the Gulf of Mexico and a little bit in the Arctic. You don't see a whole lot. There is actually some of it happening, but it's not a lot. The term ridge, of course, is misleading because the widths of 1,000 to 4,000 kilometers give the appearance of a broad, elongated swell. So yeah, if you're looking at it from space at the Earth, and you can actually use X-ray vision down to the bottom of the ocean, it would actually look like a kind of a very, very broad and not very tall ridgeline. The axis of some ridge segments exhibit deep down-faulted structures called rift valleys. And in most places, we can't actually see these rift valleys unless we send a submarine down to see them. Fortunately, there is one place where we can go to analyze these rift valleys on land. It's one place where the mid-ocean ridge in the Atlantic is actually poking its way out of the ocean, and that's Iceland. And so we can actually look at this ridge axis in Iceland, and here we see one side of it. The other side of the ridge is on the other side. There's a whole river valley. But notice these blocks here are all faulted, and they're falling in and filling in this central area. There's volcanism all along this axis, not necessarily active right in this zone that's a little further down, but you get the idea. This is a tectonically active area. Here's the distribution of that oceanic ridge system. It's all over the Earth. This is it. The Juan de Fuca Ridge is up here. It goes to the Pacific Rise. In fact, we'll be coming to this shortly, but the Juan de Fuca Ridge is actually connected to the Pacific Rise. It just happens to go underneath the western part of North America. We call that the San Andreas Fault that connects these two. But this, in fact, connects into the Pacific Antarctic Ridge, which then wraps then again all the way throughout the Western Indian Ocean into the Southwest Indian Ridge and then into the Mid-Atlantic Ridge that goes basically to the North Pole. So this is a huge structure. It's almost like a giant baseball with stitching everywhere, and that stitching is basically controlling the distribution of new oceanic crust everywhere on Earth. And so ultimately, that new oceanic crust is a kind of a proxy, or it's a way for us to look at how plates are moving on the planet. So they're really interesting and important for us to know. Here we see the oceanic floor using a color image. The colors here represent ages. And so one of the things that is kind of obvious about this is if you look at the red, notice that the red is all concentrated. This is young rock that's all concentrated right at the ridge. And then we go into zones of yellow. And notice how it's symmetric. That implies that this rock and this rock were formed at the same time, and the only place they could form is at the ridge. So at one point, these continents had to be closer together to put the yellow zones at the center of the ridge. And then you go into the green, the same thing is the case there. And look at this. In northwest Africa, this is the Atlas Mountains here. And in the eastern United States, these are the Appalachian Mountains here. There's sets of mountains that are the same age, but not only are the mountains the same age, the crust of the ocean right here and right here is the same age. So that implies that West Africa and North America at some point were all nestled real close to one another at some point in the past. And what brings about that movement? It's called seafloor spreading. So it's a concept that was formulated in the early 1960s by a guy named Harry Hess. Harry Hess was a geologist and a very, very good one. Seafloor spreading occurs along relatively narrow zones called rift zones, and they're located at the crests of the oceanic ridges. And so here we see an animation of this seafloor spreading occurring where the lava comes up, it fills the gap, it mixes. Basically, the lava is cooled by the seawater, and that makes continental crust, and then it's pulled off to the side, and it repeats the cycle. So we'll leave that animation going. As plates move apart, magma wells up into the newly created fractures and generates new slivers of oceanic lithosphere. New lithosphere moves from the ridge crest in a conveyor belt fashion, and zones of active rifting are 20 to 30 kilometers wide. And these zones aren't necessarily right where the volcanism occurs, right in the middle. Here's a crack that's quite a ways away. It's probably about 30 kilometers away from the ridge system, and I believe this is in the Southeast Pacific area. So you get the idea. This is a really active system. So one of the questions we have to ask ourselves are why are these things elevated? Why do they form mountains? If you're pulling things apart, you'd think there'd be a hole there. And the primary reason is because newly created oceanic lithosphere is hot and occupies more volume than cooler rocks. So this is hot, and therefore it rides high. It's less dense. Hot stuff is less dense than cold stuff. So this is going to sit higher than the colder version of it over here. As the basaltic crust travels away from the ridge crest, it is cooled by seawater, right? So there's seawater permeating everywhere through here, especially once it gets away from the ridge system, right? So rocks over here are much cooler than the ones that are up here. And the ones over here are very, very cold relative to these. So you can see that it kind of flattens out pretty quick. As the lithosphere moves away, it thermally contracts and becomes more dense. Okay? So that's the reason why it forms ridges. But the mountains can be actually quite tall. So it turns out that the spreading rates have a major effect on ridge topography, whether or not you get a high ridge or a nice low one. So if you have a ridge system that exhibits, in this case, a relatively low spreading rate, you're actually going to get a really nice rift valley that forms here in the middle. Okay? And it's going to be, 30 to 50 kilometers across, and it's going to be pretty deep as well, this whole system, in terms of the ridge crest and the height of the mountains. You can get volcanoes located quite some ways away, basically taking advantage of faults to feed lava onto the flanks here. And so in this case, also, we would get a kind of a poorly developed magma chamber here. Basically, it's always clogged up because there's not a whole lot of pulling apart and decompression melting occurring. So it's kind of an intermittent process. At least that's our thinking on it currently. But by contrast, if you have a really fast spreading rate, like what we see in the Southeast Pacific, where the oceanic crust is basically going from the southeast Pacific and subducting underneath eastern Russia. We see this type of structure here. And so in this case, from 5 to 9 centimeters per year, which isn't that much, by the way, 5 to 9 centimeters per year, that's between there and about there per year. But in geologic terms, that's pretty fast. Rift valleys that develop are shallow and less than 200 meters deep. This is not a very good ridge valley right here, rift valley that's forming here. Okay. At spreading rates greater than 9 centimeters per year, no median rift valley develops, and these areas are usually narrow and extensively faulted, right? So it's basically just ripping apart. You have a bunch of dikes that come in and fill it up. It doesn't really have the chance to cool down and to form a nice rift valley. And you wind up with a pretty well-developed magma chamber down here that's feeding this rock, this molten material up to the surface quite efficiently. So with that said, we now recognize that there's a definite structure that comes from these mid-ocean ridges that is inherited by the crust itself. And we can actually see this. First off, we recognize that there's going to be 4 distinct layers. There's the mantle down below, which is going to be the peridotite. The peridotite is what melts and makes the crust above it, the oceanic crust. And so these layers are very predictable. First off, you get layer 1, which is the sequence of unconsolidated sediments. That's up here. This is the stuff that's raining out of the ocean, out from top to bottom, that's flowing in from rivers and whatever. Layer 2, which is consisting of pillow lavas, located right in here. Numerous interconnected dikes called sheet dikes. You might be asking yourself, why are there dikes in here? This doesn't make sense. There might be an occasional volcano, but why are there dikes here? Well, you've got basaltic pillow lavas up here. Pillow lavas, by the way, form underwater. That's the reason, and they take on a pillow structure. We'll be showing pictures of that here shortly. But the sheeted dike complex basically forms because you have a gabbro, which is a basaltic magma chamber, and you're feeding that material up towards the water, and it's cooling. And so you wind up with these nice sheeted dikes, and we can actually see that in the picture here. Here's our magma chamber. This is eventually going to become our gabbro. Here's our sheeted dikes that are filling in. We can see them as red lines. And then up here at the top is where we're going to get our pillow basalts, and eventually sediments are going to cover all of that. And that's what we're seeing here. And it's just constantly forming this, day in and day out, year in and year out, since the formation of the Earth. Here we see some of those pillow basalts I was talking about before. Basically, the molten rock is injected into fractures above the magma chamber, and it creates a sheeted dike complex. The submarine lava flows chill quickly, and the congealed margin is forced upward to produce large tube-shaped protuberances known as pillow basalts. Anyways, it looks like this. They look like giant pillows. And here's one actually. This is off the coast of Hawaii, forming on the Loihi seamount. And I don't know exactly when this was, but it's happening all the time, actually. So you can see that's actually forming nice pillow basalts. But pillow basalts form underwater, and so that's important to note. If you find a pillow basalt anywhere on Earth, it's almost certainly that it formed underwater. So what is the nature of these interaction between the seawater and the oceanic crust? That's something that is definitely playing a major role here, and we can't move past it. We have to talk about this. We talked about metasomatism, and we kind of hit on this concept a little bit, but we really kind of need to bring it back. So really what it is seawater circulates downward through the highly fractured crust. Remember, we're talking about when you're ripping crust apart, making ridges and rifts. You're breaking deep faults down into the earth. The basaltic rock is altered by hydrothermal metamorphism, so the water comes in, it heats up, and hot water is really good at scouring out minerals and things that might be soluble in water. It's very good at it. And by the way, the pressure is so great down there that the temperatures of the water can get well above boiling up here at the surface. 300 degrees Fahrenheit is not uncommon at some of these hydrothermal vents, I should say. And so these hydrothermal fluids dissolve ions of various metals and precipitate them on the seafloor as particle-filled clouds called black smokers. When it's cold water, it can't hold as much material in it. When it's heated up, it's able to pick up a lot more. Material becomes more soluble in it. But once that hot water hits the cold water up here, it immediately gets cold and suddenly it can't hold all that material anymore. And so that black smoke, or that all that material, starts to precipitate out. We can actually see hot water coming out, and it's immediately starting to rain out that black mineral gunk all over the place. But this mineral gunk is actually pretty valuable stuff. Manganese, for example, and barium, things like that. Minerals that are hard to get up on the Earth's surface economically. Of course, every ocean has a start by breaking a continent. That's just kind of the way that it works. It's not the other way around. Continents don't form from the breaking of oceans. It's the other way around. And so in order to form an ocean, you got to break up a continent, either a supercontinent, or you can even break up the continents that exist. And so in this case, a new ocean basin begins with the formation of a continental rift. So here in East Africa, there's actually such a rift forming. The Red Sea is already broken off. Here we see the Gulf of Aden that connects all of it in. But the Afar lowlands that connects all the way around Lake Victoria and past Kilimanjaro, all the way to the western part of Madagascar, which is already rifted off, is basically trying to break all this material off into the Indian Ocean and create a new ocean basin behind it. So this splits land masses into two or more smaller segments, but it also creates oceans behind them. So typical examples are the East African Rift, that's what this is here, the Baikal Rift, which is up north of Mongolia in Eastern Asia, the Rhine Valley in Europe, the Rio Grande Rift, that's where basically right where Albuquerque, New Mexico is. And the Basin and Range is another example, eastern Nevada and western Utah. The Red Sea is an example of a rift valley that has lengthened and deepened in a narrow linear sea. So it's actually moved into the next phase. So it's broken the land apart. So here we see Saudi Arabia, actually Yemen. Saudi Arabia is up here in the desert to the north. And the East African countries, I'm not sure which one this one is specifically. It's probably Egypt. Has rifted away in this zone. And of course, the basin is just going to develop over time. You know, this is exactly what happened between Africa and South America. So here's Africa, here's South America. Basically, at one time, they were close together, and this is what started happening between them. Now we see a well-developed ocean basin where we got the rift valleys, the mid-ocean ridge, we got the abyssal plains, and we even got passive margins on the edges of the continents. So there's nothing new here, right? We can actually follow the whole cycle around if we wanted to. It's really neat stuff. But not all rifts work. It turns out there are failed rifts all over the world, and some of them are really economically valuable. For example, the rift zone up that we're going to be talking about here in Michigan. So a failed rift valley extends from Lake Superior into Kansas all the way up into here. So Lake Superior is a failed rift all the way through here. The formerly active rift valley is filled with basalt and clastic sedimentary rocks. When I say clastic, remember detrital, clastic are kind of hand in hand the same thing. Sandstones, conglomerates, siltstones, and shales. Why rifts fail or succeed is not fully understood. We know that sometimes they happen and sometimes they start and then they stop and then they never activate again. This is one such case where the history of this suggests that it is not going to be active anytime soon. It's kind of interesting, actually. But here we see our volcanic rocks in the middle, and they're surrounded by sedimentary rocks on the outside. So we have been kind of avoiding the, the $64 question here. Why? Why does oceanic lithosphere subduct? There's two ways that you can make it happen. There's the spontaneous subduction, which is where it's just so old and thick and dense that it sinks by its own weight. It wants to go down. And the result is that you get a descending angle of nearly 90 degrees. And a classic example is the Mariana Trench. That's also where you get the deepest trenches, right, is in this environment. So in other words, the oceanic plate comes up to the continent or whatever is forcing it to subduct, and it basically hangs down like this. And so as it hits, it just starts to fall at nearly 90 degrees. The lithospheric mantle is what drives subduction, okay? Forced subduction is a little different. This is where younger, less dense lithosphere is forced. In other words, it wouldn't sink on its own beneath the overlying plate by compressional forces. This descends at shallow angles, for example, the Peru-Chile trench. So in this diagram here, we can actually see those angles played out. Right here we have an old, cold oceanic lithosphere. This is something that wants to subduct. It's pretty old by the time it gets over here and it wants to fall into the ocean. Gravity is trying to pull it down. You get a nice arc in a trench. The trench is going to be quite deep. If you wind up with young, warm, buoyant lithosphere, it has a hard time subducting. It doesn't necessarily want to go down in below the asthenosphere. It doesn't want to go down very, very rapidly. And in fact, it can go at a very shallow angle. And it creates very interesting tectonic consequences, some of which can be quite hard to work out. But nonetheless, there's a variety of angles, and it's usually dependent upon the age or the manner in which it is approaching the trench. So it turns out that not all plates on Earth are long for the entire duration of Earth history. About 180 million years is about the oldest that we find our oceanic plates. Continents, we find rocks that go back to almost 4 billion, and some people are convinced they find parts of rocks, a mineral called zircon. They think that they found zircons that actually predate that and go all the way almost to the origins of the Earth itself, about 4.3 billion years old, 4.2 billion years old. There's a lot of controversy about what they're getting out of that or out of these zircons, but the fact that they have rocks that old and that they're in the continents kind of tells you something about the continents themselves. But one thing that we can be assured of is that the oceanic plates come and go all the time, right? Or the oceanic crust comes and goes all the time. Sometimes it's part of a continental plate and sometimes it isn't. Sometimes it adds itself and sometimes it doesn't. And one such classic case is the Farallon plate. So the Farallon plate once occupied much of the eastern Pacific Basin, basically the area off the coast of what we now call Los Angeles and San Francisco. So here's the Farallon, here's the Pacific plate. And eventually the plate got continually smaller and now only fragments of the original plate remain. So here we see over time the North American plate, the Pacific plate got closer as the subduction zone kicked off. Subduction zone made the plate smaller, and now this is what we find today, that there's really actually two separate plates. There's the Cocos plate down here that's subducting beneath Mexico, and there's the Juan de Fuca plate here. What is connected between these two as the Farallon plate has subducted and connected these two, or disconnected these two? A new fault has formed, and that fault is the San Andreas. So the San Andreas fault is actually located at approximately the same position as the old subduction zone of the Farallon plate. So the different types of margins start to form. In this case, the Pacific plate and the North American plate the Pacific plate does not subduct beneath the North American plate. There's actually transform fault boundary that has developed here. And here we can see it. It's the San Andreas fault. All right. I highly recommend a video. The video is located at this YouTube web address, especially the first 19 minutes, and it will kind of sum up a lot of the things we've been discussing in the last couple of lectures. So anyways, I know there's a lot of information here, and hopefully it wasn't too dry, but I think it kind of explains a lot of what's kind of powering plate tectonics at the surface of the Earth. So watch the video, and by all means, if you have any questions or concerns, find me on the discussion boards or send me an email. Until next time, I hope you have a really good one.